With this lecture, I want to establish a basis for inference principles. We're going to focus on inference of one population to establish the ideas of confidence intervals, hypothesis testing, and p-values, which we can then leverage on when we get to regression settings. The ideas just carry through. Our challenge in statistics is working with a subset of information, a subset being a sample from a larger population, and trying to do our best to infer something about that population. So as you can see here, I have a sample on the left with statistics that we can extract from the sample, the mean, the variance, and we're using these to infer the unknown or hidden population, to infer what is the shape of the population, what's the mean of the population, what's the variance of the population. So here's the great challenge. The great challenge is that sample statistics will change from sample to sample. Whatever I get in a given sample, I'm not going to get in another sample, even if it's from the same population. Imagine randomly picking individuals from the state of Wisconsin and looking at their incomes. I pick 100 people from Wisconsin. I find all their incomes. I get an average income. And then let's say I get another random sample that's going to give me, indeed, a different Y-bar, a different sample variance. Sample statistics are random. They have probability distributions. We call them sampling distributions. And our challenge is to use the sampling distributions to infer something about the population. Now, we're always going to live with uncertainty. Unless we have the full population, we can never say anything with certainty when we're dealing with statistics and data. To get an idea of a sampling distribution, let me use an applet that's on the internet. It's a really nice one from Rice University. You can use this link or just Google Rice Virtual Lab and Statistics. I'm going to the Simulations Demonstration section. I chose the option to explore the sampling distribution of the mean. Now, on the top, you pick your population. You can choose a skewed distribution, a normal distribution, but I chose to customize the population. And I did that so that I can create the most non-normal looking population that is completely whacked out to show you the power of what we're going to learn called the central limit theorem. I chose the option of choosing 25 observations from the population, and then it would compute the average, and we'll do that repeated over and over again. Here is the first sample. 25 observations were taken from this crazy population. Here are the 25 observations recorded. And then the average of these 25 observations is recorded down here. This is just one sample average. To get the sampling distribution, we're going to need to do this experiment over and over and over again. Here's the result of doing that experiment over and over and over again, namely another 10,000 times. So I have the one from the previous slide, 10,000 more, so I have in total 10,001 Y bars. And look at what we get. We get a sampling distribution of Y bars to be spot on with the normal distribution, even though the population is nothing close to the normal. There's something remarkable happening here. Notice also that the population mean is 19.80 and the average of the 10,001 Y bars is 19.80. No accident. Let's do it again, but let's focus on the standard deviation. Here's a completely non-normal population distribution again. The standard deviation of the population is 8.00. below I get 220,000 Y bars based on N of 10 and 220 Y bars based on N of 25. Again, both sampling distributions for the sample mean are normally distributed, which is a remarkable result. In the case of N equaling 10, the normal distribution is a little wider than N equaling 25. And that's something we expect. The larger the sample size, the tighter the sampling distribution will be. Let's compare with this number of 8 for the population, which is sigma, the population standard deviation. We find for the sampling distribution based on N equaling 10, standard deviation is 2.53. Is that an accident? No, it isn't. In fact, if we take sigma, which is 8, divide by the square root of the sample size, which is the square root of 10, we get 2.53. Same thing here for 25. The standard deviation of the sampling distribution of Y bars when N is 25 based on the simulation is 1.60. Take a look here. Sigma over the square root of N is 1.60. None of these are accidents. I actually knew what the standard deviation would be without running the simulation. The simulation just confirmed what I knew, namely these formula. What have we learned? We learned that the sampling distribution of the sample mean is basically the normal distribution, regardless of the shape of the population. This is called the central limit theorem effect. It states that if we randomly sample from a population of any shape, the distribution of the sample mean is basically going to be approximately normal, with the approximation getting better as the sample size gets larger. We also know that the mean of the sampling distribution, the mean of the Y bars, is equal to the mean of the population, mu. We also know that the standard deviation of the sample distribution, the standard deviation of Y bar, is theoretically equal to sigma over the square root of N. Now that means the variance, if you square this, is sigma squared over N. Thus, we can summarize everything down below by stating Y bar is normally distributed with mean mu and variance sigma squared over N. Now that we have this idea that sampling distribution is the result of sampling over and over and over and over again and recording the possible sample statistic values, let's look at the sample variance. And it will give us a hint why we indeed use n-1 in the denominator, as when I first introduced you to the sample variance. Let's consider a population with some mean mu. It's pretty irrelevant. I'm choosing 200 and a variance of 100. I'm going to randomly pick 10 observations from this population. I'm going to calculate two different statistics. One based on the sum of yi minus y bar squared over n minus 1. In this case, over 10 minus 1, as you can see here. And then the other being over 10, simply over n. What we probably would have thought we should have done. It's more intuitive, I would assume, to divide by n, not this notion of n minus 1. Now, I want you to recognize just algebraically that this way of dividing by n, and I'll call it s bar squared, is really, algebraically, you can work it out, is just 9/10 of s squared. So remember that. Here are 50,000 s squareds calculated in the way of dividing by n minus 1. Notice it's not a normal distribution, so this is not central limit theorem related. Remember that the population variance from the previous slide is 100. We see samples where the estimated variance is less than 100 and estimated also to be greater than 100. But if we were to average all these 50,000, you'll find it to be actually 100. That means on average, the formula of dividing by n minus 1 is on mark, on target with the true variance. Realizing that the alternative statistic of S bar squared is based on dividing by n and is 9/10 of the other statistic, we then realize that the average of 50,000 S bar squared values would be 90, which is not indeed the true variance. This is to show you that dividing by n minus 1 gives you a statistic that on average is on mark. We call such a statistic an unbiased estimator. Here's a summary. Dividing by n gives a biased estimator of the variance parameter. Dividing by n minus 1 gives an unbiased estimator. Now, n minus 1 is referred to as degrees of freedom. Let me just give you a quick sense of why we call it that term. Suppose n is 3 and y bar is 10, as you can see here. Well, you know if y bar is 10 and n is 3, then the sum of these three observations must be 30. If I were to tell you the first observation is 8 and the second observation is 3, that would mean the sum of these two would be 11. That forces the third one to be 19. There's no choice here. There's no freedom to be anything other. This third observation is locked in. So only 2 out of the 3 are free to be whatever they might be, and the third one is determined by the other 2. That is 3 minus 1 degrees of freedom, or in general, n minus 1 degrees of freedom, because n minus 1 of the observations given a y bar determine the nth observation. Now later we will see other statistical methods might have n minus 2 or n minus 3 degrees of freedom. Here's a simple trick to remember how many degrees of freedom you will use. If we had known the population mean, it turns out that given a sample of n observations, that if I take y minus mu, square it up, add them all up, an unbiased estimator would be dividing by n. But here's the key point. I don't know mu. For every parameter we don't know and have to estimate in the variance formula, we lose a degree of freedom. So the fact that mu was replaced with y bar is why I lost a degree of freedom. Every parameter you have to estimate, you lose a degree of freedom. Just remember that when we have to have more than one parameter in future applications. We've learned that the sample mean serves as an estimate for the population mean because remember the sample mean y bar on average, the sampling distribution is equal to the population mean mu. So it's an unbiased estimator. It's really the right choice as your single point guess for the population mean. Now, suppose we have a situation where y bar equals 550. Well, as I said, this is a single value estimate. It's a point estimate. It gives us our best guess, but it conveys little information on how close we might actually be to the population mean. We want to come up with alternative ways of reporting estimates. Instead of a single estimate, we might report a range. We might have a statement like, we're 95% confident that mu is in the range of 500 to 600. We might be 99% confident that its mu is in the interval of 485 to 615. Obviously, to be more confident, we're going to have a wider range. But this gives you a better sense of how close we might be to the true population mean. It's incorporating the variability in the data. Now, to get to these confidence intervals, let's take stock of some theoretical results. From the central limit theorem, we learned that y bar is distributed basically normal with mean mu and standard deviation sigma over the square root of n. That means if I were to take y bar and rescale it as follows, y bar minus its mean divided by its standard deviation, this will give us a random variable which we call z, and we've learned this in earlier lecture, that is a standard normal random variable that follows a normal distribution with mean 0 and standard deviation 1. Now, one problem here is that I don't know sigma because we're dealing with data. So I'm going to replace sigma with my best guess, the sample standard deviation. What we now have is y bar minus mu over the sample standard deviation divided by the square root of n. Turns out that this ratio doesn't quite follow the z distribution. It's close. It follows what we call the student's t distribution, or t distribution for short. That's why I'm using the letter t here. And in particular, it follows a student's t distribution with n minus 1 degrees of freedom. It's important when you deal with the t distribution to know the degrees of freedom. The n minus 1 is embedded in the s.
Here's what the student t distribution looks like. It looks very much like a normal. It's bell-shaped. You'll note here that the z distribution is in the one in red. When the degrees of freedom are smaller, the t distribution tends to have thicker tails than the z distribution. As the degrees of freedom increase, the t converges to the z. By 30 degrees of freedom, it's almost there. And thus you hear in stat books often that you can use the z in place of the t when the degrees of freedom are 30 or more, which is fairly true. I will tell you theoretically the t never becomes the z until the degrees of freedom are infinite, but it's close enough for 30 and above. But with that said, software will always use the more precise t rather than an approximation. So we'll want to focus on precision moving forward.
Now, given the closeness of the t and the z, we can use our rule of thumb we learned earlier for the normal distribution. Namely, if we're within 2 standard deviations of the mean, we get about 95%. So if the sample size is large enough, let's say giving us degrees of freedom of 30 or more, the t is essentially the normal. And we have the probability of the t falling beyond plus or minus 2 to be also about 95%. Here you can see that statement being given with y bar minus mu over s over the square root of n. That's a t. The probability it's between minus 2 and 2 is about 95%. Now, if we were to rearrange the interiors within the parentheses, we can write it as follows. Y bar plus or minus 2 times s over the square root of n. This is a confidence interval on the mean. It's a approximate confidence interval, but it gives us basically approximately the plausible values for mu. Now, if we want to get to the confidence interval precisely as software reports it, we realize that we have to use the t distribution. Here is a t distribution, and I generically have a critical value, which I'm calling t star, and the symmetric minus t star, to encompass an area 1 minus alpha. So this is just approaching the confidence interval in generality. And I want to find the t star such that the probability the t statistic falls between minus t star and t star gives me 1 minus alpha. That means in the red area in totality we have alpha, and then on one side alpha over 2. If we could find t star, and we can, and rearrange the inner quantity found on the previous slide, we get the confidence interval looking like this. Y bar, our best guess for the population mean, plus or minus T star times S over the square root of N. Now, each one of these are given names. S over the square root of N is called the standard error of mean estimate. It measures the uncertainty of our estimate. The larger it is, the more uncertainty we have about the estimate for the population mean, and it will result in a wider interval. You can see that it's a function of a couple things. It's first a function of n. The larger n is, the smaller the standard error is, and that makes sense. More information reduces uncertainty. It's also a function of S, the variability in the data. The more scatter we have in the data, the more variability we have, and thus the more uncertainty we have. So the larger S is, the more uncertainty we have. This all makes sense. Now, when we take T star times the standard error, we get something called the margin of error. So a confidence interval breaks down to a best guess plus or minus margin of error. Now remember, T star comes from a T distribution with n minus 1 degrees of freedom. Let's consider an example. Suppose manufacturing pulls a random sample of 20 parts where the part is a brake disc rotor that is specified ideally to have diameter 330.2000 millimeters. Nothing in life is going to be exact. There's going to be variability. And we can see here the 20 rotors with their diameters. We see the variation. The question ultimately will be, do the rotors from this sample reflect a larger population, a process that is on mark with the mean of 330.2000?
Let's first look at the histogram of the data. The individual observations look fairly normal. Now, we do have the central limit theorem to protect us if the underlying population is not normal. But since we only have 20 observations, we have more confidence in the central limit theorem, given that the sample seems to be coming from a population that is fairly normal. We find Y bar to be 330.20269, and we find the standard deviation reported below.
As I said, ideally the process mean is on the specification of 330.2000. Our best guess is that mu is 330.2027 rounded. So does that mean the process is off target? Well, not necessarily, because we realize that Y bar fluctuates. And this could just be within chance variability or chance fluctuations. An approximate 95% confidence interval is taking Y bar plus or minus twice S over the square root of N, which gives us a range from 330.1982 to 330.2072. We see that 330.2000 is inside the range, so it's a plausible value. There's really no evidence to suggest that the process isn't on mark. Now let's do this precisely, not use the rule of thumb. Let's get T star. And what we want to do is look at a T distribution with 19 degrees of freedom, because that's 20 minus 1. And I want to find this T star value that gives me 95% in between, to give me a 95% confidence interval. That means there's 2.5 over on the left side, 2.5 over on the right side. Now I'm giving you a perspective that we see below here, because a lot of software will use this perspective for our finding of T star. If 95% is in the middle, and 2.5 is over here on the left, then that means T star is associated with a total area to the left of it of 95 plus 2.5 or 97.5, 0.975. So we want to find that value, a T star with 0.975 to the left of it. Here's why you need to know that perspective. If you're using Excel, you would use the T inverse function, and notice I'm entering 0.975 and then the degrees of freedom, and it comes back and says the T star is 2.093. The jump calculator, we can actually find it several ways. I'm using the everything to the left option, 0.975, and we get the same value of 2.093. You could also use the right tail. In that situation, you would put what's everything to the right of T star, 0.025. You can use central. What's that? That would be everything in between 0.95. I'd ask you to explore this on your own so that you can see that you can get the 2.093 in many different ways. So we take Y bar of 330.20269 plus or minus this very precise T star value of 2.093024 times S over the square root of n, the square root of 20. And we get this confidence interval, this 95% confidence interval. And you can see from the jump output, that's indeed exactly what jump is reporting, these two values. So this is the precise confidence interval based on the T distribution. What about Excel? Well, if I use the tool pack and the descriptive statistics option, I can give a 95%, you can see that here, and dump the output, and we get the following output with descriptive statistics, and at the bottom we find confidence level. Now we don't see an upper and lower value, we see just a single value. What is that single value? Well, if you take your calculator out and take this T star times S over the square root of n, which I boxed off, which is the margin of error, you see that's what Excel is doing. It's reporting the margin of error. Thus, what we have to now do in the Excel spreadsheet is take the mean minus and plus this thing in the box to get the confidence interval that jump reported and what we manually calculated.
Now there's a nuanced interpretation of the term confidence interval. It is not accidental that it's not called a probability interval. So when we have a 95% confidence interval, as we had here for the rotor process, it's actually incorrect to say the probability is 95% that mu is in between these two values. The issue is that mu is not a random variable. It's a fixed parameter. After the data are collected and the interval is formed, mu is either in this interval or not. Now I understand we don't know, but we can't treat mu as a random variable. It's actually correct to say that over repeated samples, 95% of confidence intervals constructed will include the true mean mu. Thus, we can only say how often such intervals may include the true mean. That is what confidence level is all about.
Okay, let's talk about proportions. Recall the sample proportion is computed as the number of successes divided by the sample size. So for example, in the not drinking cola versus drinking cola, we had 1,000 for N, 422 do not drink cola, so that's a sample proportion of no being 0.422, 578 out of 1,000 is a proportion that do drink cola, 0.578.
I want you to recognize something about proportions. They're actually sample means. Let's think about that for a moment. Suppose we have 10 units sampled from a manufacturing process and units 3 and 7 are defective. What proportion of the 10 is defective? Well, it's 20%. But consider it from this perspective. Suppose I assign a value of 1 to a unit that's defective and a value of 0 to a unit that's not defective. Then you can see below here, if I take the average of those 0 and 1 values, I would have 0 plus 0 plus 1 plus 0 plus 0 plus 0 plus 1 plus 0 plus 0 plus 0, which is 2 divided by 10, which is in the end 0.2. So the sample proportion in the end is nothing more than the sample average or sample mean of zeros and ones. But we learned earlier that the sample means are approximately normal due to the central limit theorem if your sample size is large enough. That would mean that the sample proportions will be approximately normal for large enough samples.
Well, we can also determine the standard error. This is a little unique from the S over square root of n formula, but it turns out, and just trust me on this, that the standard error for the sample proportion is going to be p hat, that's times 1 minus p hat over n, then take the square root. So that means that if the sample proportion is approximately normal, the 95% confidence interval would basically be p hat plus or minus twice the standard error.
For our cola example, let's look at the sample proportion of cola drinkers. P hat equals 0.578. So the standard error is 0.578 times 1 minus 0.578 divided by 1,000 and then taking the square root to get a standard error of 0.01562. Using our rule of thumb, we can get the approximate 95% confidence interval of 0.578 plus or minus 2 times that standard error to give us a range from 0.547 to 0.609. What can we infer? Well, we can infer that the population proportion of cola drinkers is probably greater than 50%. I also want you to notice something interesting here when dealing with the proportion. Notice the margin of error is about 3%. If you probably give it a little thought and think about surveys, whether on TV or internet, you will often hear a margin of error of around 3%. This is indeed that guy. Basically, when you're dealing with sample sizes are in that sort of 500 to 1,000 range, which is very typical with surveys, getting a 3% margin of error is about what you'll often get. Here's the jump reporting of the confidence interval from the Analyze distribution platform. You can get the confidence interval option from the red arrow pull down. You see it here. It's basically the numbers that are on the previous slide, but jump is being more precise in its multiple. It's not using 2, it's using something like 1.96, and there's some Euler nuance tweaks behind the formula, but it's basically what we got.
All right, so that's a confidence interval. That's inference of population parameters like mu and the population proportion. Best guesses being y bar and p hat. Going beyond best guess, a confidence interval. We can use this knowledge now to talk about hypothesis testing, which I'm sure you've heard of when it comes to statistics. What is a hypothesis? A hypothesis is a statement about a population which is developed for the purpose of indeed testing. We have two competing hypotheses. A null hypothesis, often denoted by H naught or H0, it's a statement about the population parameter or parameters that we assume, and this is critical, we assume to be true unless there's sufficient evidence to the contrary. The alternative hypothesis, H1, is just the contrary to the null. If there's evidence that H naught is false, thus we accept the alternative. That's the establishing of the hypotheses. The other thing we do is establish what is called a significance level. Often you might hear significance levels of 5% or sometimes 1%. This is a threshold to determine whether or not we think the evidence is strong enough to suggest the null hypothesis is not true. From the data, we get what's called a p-value, or we construct a confidence interval. With these, we can then state a conclusion. We're going to see in a moment that if the p-value is less than the threshold alpha, we reject the null. If it's greater than alpha, we conclude that there's not enough evidence to reject the null. If we use a confidence interval, if the confidence interval does not include the hypothesized parameter, we reject it, the null hypothesis. If it does include the hypothesized parameter, then we don't have enough evidence to reject the null.
Remember, without complete information about the population, we will always be living in a world of incomplete information. That is, we are making decisions in a world of uncertainty. As such, we are always at risk to make a wrong decision. As the table shows, there are two types of wrong decisions, namely rejecting the null hypothesis when we shouldn't have. This is called a type 1 error right here on the table, and failing to reject the null hypothesis when we should have. This is referred to as a type 2 error. The significance level alpha can be interpreted as the type 1 error rate. It is the level that you're willing to accept in terms of the rate, the probability of rejecting the null hypothesis when you shouldn't have. Let's go to our brake rotor example. The specification is 330.20. Let's say that we want to test if the underlying population mean for the process is indeed mu equaling 330.20 versus not the alternative. We are concerned about the process making parts too big or too little. Either way is a problem. As such, we are interested in detecting departures from 330.20 in either direction. This hypothesis testing setup is referred to as a two-sided hypothesis test.
We'll assume the null to be true. This is key. Always assume the null to be true. That establishes a reference, and we're going to see where the data falls relative to that assumption. We compute an observed t-statistic, which you recall is y bar minus mu, but here the mu is the hypothesized value, which we're assuming the population mean to be, and I'm calling that mu 0, divided by the standard error, s over the square root of n. So in this case, y bar of 330.20269 minus the hypothesized mean divided by the standard error gives us a t-statistic value of 1.1917. Basically, we can interpret the result as follows. The observed y bar of 330.20269 is sitting about 1.19 standard deviations away from 330.20. The question you have to answer, is that unusual? That's the question we want to answer.
Here we can visualize our result with a reference. If the null hypothesis is true, then our t-statistic should fall somewhere under this t-distribution with 19 degrees of freedom. It fell right here, which is well within the fray of things. I'm moving my pointer from -2 to +2, where we would expect 95% of the time this t-statistic would fall if the null hypothesis is true. We have to recognize that variation occurs. The question is this 1.19 in light of variability occurring unusual? Well, again, given that it falls within this range here of where we expect 95% of things to fall, I would not really view this as any evidence here to reject the null hypothesis. That's the idea behind hypothesis testing, seeing how unusual or not the observed test statistic is relative to where we would expect things to occur if the null hypothesis is true. Now we're going to translate things into what is called a p-value. A p-value is the following. If we assume the null hypothesis is true, what is the probability of observing a value as extreme or more extreme than that observed? That sounds a little confusing. Let's look at a picture again. We observed 1.1917 for our t-statistic. Now remember, we're looking at a two-sided test, so we're concerned about departures in either direction, to the right or to the left. Thus, formally, this test is considering the t-statistic in absolute value. When calculating the p-value, we must consider the departure on the positive side and the negative side of 1.1917. As such, the p-value is this grayed area to the right of the plus value and to the left of the minus value. We find the p-value to be 0.248. Now, recall that getting a observation, let's say, greater than 2 in absolute value would be beyond the 95% range. As such, the p-value would necessarily have to be less than 0.05. This is leading us to a decision rule.
Before we talk about a decision rule, let's first calculate this p-value as I showed you on the previous slide to be 0.248 using the distribution calculator in JUMP. I'm going to the t-distribution, as you can see here, with 19 degrees of freedom. I'm giving the values of minus 1.1917 and plus 1.1917 and asking JUMP to give me all the area beyond those values. And you can see indeed it reports back 0.2481. That's the p-value.
Well, we've manually found the p-value after manually computing the t-statistic. We can actually have JUMP do all of this with a couple button pushes. If we go to Analyze Distribution Platform, we will find under the red arrow option the test mean option. We give the hypothesized value right here of 330.20. We don't know the true standard deviation, so we leave it blank. We click OK. Here is the output. We see that JUMP reports what we manually calculated. The test statistic is indeed 1.1917. We look at the p-value here associated with the absolute value because it's a two-sided test, and it's reported to be 0.2480. Now we got 0.2481 a couple slides back, but that's just rounding error. I'll note to you, Excel amazingly provides no convenient option to perform this ever so simple one sample t-test. I'm just shocked by that, but it just doesn't.
Let's lead to a general decision rule. Let's realize the farther out the test statistic is, either farther out in the positive direction or negative direction, the more inconsistent the observed value is with what is expected under the null. And the farther out the t-statistic or test statistic is, the smaller the p-value because there's less area out there. So if you put this all together, you realize we reject with small p-values. The threshold alpha is chosen to be small. It's called our significance level. And as I mentioned earlier, typical p-values for historical reasons are 0.05 and 0.01. So we have a basic rule. If the p-value is less than or equal to alpha, we say the data result is statistically significant at level alpha and we reject at that level. So you see here the rule, reject H naught if the p-value is less than or equal to alpha, and we say that the data result is statistically significant at level alpha.
For an alpha of 0.05 and a p-value of 0.248, we cannot reject the null hypothesis that the underlying mean dimension is 330.20 at the 5% level because the p-value is greater than alpha. Think about it this way. We have a p-value that is about 25%. And the implication is that 25% of the time, we're going to get results like what we have observed if the null hypothesis is true. That's not an unusual result. It happens, and it happens quite often. We have nothing here that really suggests, wow, the evidence is strongly suggesting that the null is not true. Now, if our p-value is really small, let's say a p-value of 0.002, this only happens 2 in 1,000 times if the null hypothesis is true. That's a pretty rare event. What is that telling us? That's saying getting that data result that is associated with a p-value of 0.002 is a pretty rare event, and if the null hypothesis were true. This leads us to questioning the credibility of the null, leading us to reject the null. There is a subtle point when it comes to the proper interpretation of a p-value. Many people make a mistake in the interpretation of a p-value, and I'm including scientists and PhDs doing research. A p-value is not a measure of the likelihood of the null hypothesis. It's absolutely incorrect to say the probability is 0.248 that the null hypothesis is true. The p-value is the probability that the data result is as extreme or more extreme given the null is true. So the null is anchored down. We don't talk about probabilities on the null. We talk about probabilities on the data result given the null is true. It's subtle, it's nuanced, but you have to recognize that. As a result, if the p-value is large, then our data result is not unusual given the null, so we do not reject the null. If the p-value is small, then the data result is unusual given the null, so we reject the null. In the end, it's a binary decision, reject or accept, based on the probability associated with the data result. Now, I said the decision rule is binary. Namely, if the p-value is less than alpha, we reject. If it's greater, we don't reject. But let's not fool ourselves. There's no magic behind the value of 0.05 precisely. Actually, 0.05 has historical roots to a guy named Sir Ronald Fisher that happened to choose 0.05 because he thought it's a number that just feels right, literally that. And it's become standard practice. Why not 0.051? Why not 0.049? I think you get my gist here. Are we saying that 0.049 is rejecting and we're all happy about finding some strong evidence against the null? And versus had we gotten 0.051, we don't reject, oh gosh, too bad? Obviously, that's pretty silly. We have to have a bit of common sense here and not think of things as absolutely binary or having a cutoff that is so literally black to white at that threshold.
What I'm trying to say here is that p-values should be looked at more holistically on a spectrum. Namely, if we get p-values that are sort of up here, and I'm just being fairly vague about that, just, sort of up here around the 0.1 or larger, they're large. There's not much evidence here. But if we get a p-value sort of around 0.05, a little to the left, a little to the right, then we're getting evidence, suggestive evidence of rejection. When the p-value starts getting smaller, though it says here moderate, but we're pushing here at the 0.01 and less than that, then we're really getting convincing evidence. So it's really a spectrum. Just use common sense when you see your p-values. Now, it's often going to be pretty obvious. You get a p-value, let's say of 0.0001. I mean, whatever your alpha is, it doesn't really matter. That's strong evidence of rejection. Your p-values are 0.4, 0.5, 0.8, or whatever. That's not much. You're going to basically say, we don't have evidence. We don't reject. In most cases, it's going to be pretty obvious. Now, I will say, I'm going to stick to the script of saying my p-value less than 0.05 reject and greater than, but don't think I don't understand the holistic perspective as I'm saying here. As I mentioned earlier, you can use the confidence interval to reject and accept nulls because our confidence interval goes from 330.197 to 330.207, and that includes the null hypothesis of 330.20. We cannot reject the null hypothesis at the 5% level. The same conclusion as the p-value. Understand that confidence intervals and p-values are internally consistent. They can never contradict each other. As long as you're using the same alpha for a baseline for a p-value approach as the alpha in the construction of the confidence interval. It doesn't matter. It's just a matter of perspective.
Let me give you some exposure to hypothesis testing for the proportion. We're not going to go too deep, but I want to also show you through this example how one-sided tests are done. Suppose we have a question of, is there evidence that more than half of the British population drink cola? We're not going to simply ask, is it 50% or not? That would be two-sided. In this case, we're going to go one direction. The null hypothesis is 50%. To be complete, we could say 50% or less, but the question is in the alternative, is the proportion of the British population drinking cola greater than 50%? Now, the test statistic, based on the fact that the proportion is approximately normally distributed for large enough sample sizes, is to get a z, and that is computed by taking the observed proportion minus what you're hypothesizing. That's the benchmark in the null hypothesis. So in this case, it would be 0.5, dividing by the square root of the hypothesized value of 0.5 times 1 minus that hypothesized value divided by n. This is a standard of error for the sample proportion under the assumption that the true proportion is at 50%. Now recall, the sample proportion equals 0.578 and the sample size equals 1,000. So the observed z is shown here, calculated to be the difference between the sample proportion and the hypothesized, null hypothesized value of 50%. Divided by the standard error, and we get a z statistic of 4.9332. Immediately we realize that's well beyond 2 or 3 standard deviations, so that's clearly a significant result. But let's formally show you how we do one-sided testing. With a two-sided test, the p-value was computed by getting all the area to the left plus all the area to the right of a certain departure of the observed test statistic. With a one-sided test, we only compute the p-value in the direction of the alternative. In this case, the alternative is greater than, so the p-value would simply be all the area to the right of the observed z statistic of 4.933. Here in the distribution calculator, I'm getting a z distribution. I'm giving the value of 4.933 2 to be more precise. All the area to the right of it, JUMP reports a very small p-value. It doesn't give it exact. In Excel, I can find that exact value by taking 1 minus all the area to the left of 4.9332, and we find that p-value to be 0.00000404466. So a very, very small p-value. We resoundingly reject the null. Instead of manually calculating the z-statistic and then going to distribution calculator, we can have JUMP do it all. I'm going to go to Analyze Distribution Platform, give the COLA variable. We get the breakdown here in terms of counts and probabilities. I'll go to the red arrow option, which is right over here on the left, and choose the test probabilities option. When I do that, I get the dialog boxes you can see here. I give 0.5 and 0.5. I choose the second option of greater than because I'm doing a one-sided test. Here is the result. It tells us that for the one-sided test, we get a very small p-value, which is what we got. However, note it says a binomial test. This turns out to be a more precise testing than using the z-statistic. To get the probability in more detail, I can click on this value, and then there is a format option to report to a certain number of decimal places. I report to many decimal places, and so here's the exact p-value based on the binomial test. It's 0.000000045, which is identical essentially to the normal approximation p-value we got. So we essentially get exactly the same results. Given the extremely small p-value of 4 times e to the minus 7, that means bringing the decimal place over 7 places to the left, gives us extremely strong evidence to reject the null hypothesis that the population proportion of cola drinkers is 50% or less. Thus, we have strong evidence to conclude that more than half the British population drink cola. We have been focused on statistical significance, and we will continue to do so, but it's really important to touch base on this idea of practical significance. Here we have output on 1 million observations, which are coming from a normal distribution. Suppose we are interested in the question of the population having a mean of 100. It sure looks that way, with the average being 99.995663. However, the 95% confidence interval doesn't include 100. The testing of mu equaling 100 gives a test statistic of more than 4 standard deviations away with a corresponding small p-value. The thing that's happening here is that we have so much data that we can pick up even minuscule departures from the null. Thus, we do have statistical significance. We have evidence that mu is not equaling 100. The question is that of any practical importance? Now, maybe in high precision manufacturing for parts to NASA, being off by the smallest of amounts is really a big deal. But probably in most applications, the ever so slight departure from 100 is not a big deal. Realize in general, when you have a lot of data, you'll often get statistically significant results. It's just because of having so much data. You have to again answer the fundamental question. Is it a practical importance? Only context can answer that. To round out our lecture on inference, let me expose you to an approach of getting a handle on the sampling distribution of a statistic in question if we are not comfortable with relying on the central limit theorem effect. This approach is a modern day idea made possible with computing, and an idea which we will want to remember for a procedure much later in the course. It's called bootstrapping.
Well, what if we don't have the necessary mathematical results to determine the sampling distribution for a particular statistic? One scenario would be, for example, what if your sample size is not large enough to lean on the central limit theorem? Or what if we have a statistic that we just don't have grasp on mathematically? Theoretically, one possibility is to repeatedly sample n observations from the population, computing each time the sample statistic in question, collecting many samples, millions, let's say, and construct the sampling distribution. Well, that's not a realistic solution. We can't keep sampling from a population that's timely, that's costly, and it's just not realistic. We only have one sample. And in the past, we only have one sample, but we leaned on mathematical results to get us to the next step. What do we do here? So how do we know how much sample statistics vary if we only have one sample and we don't have a mathematical backing to give us the answer? Well, in the 1970s, a Stanford University statistician named Brad Efron came up with an ingenious suggestion. And it was a suggestion that initially the community, the statistical community, says, no way would that work. He suggested treat the data as a proxy for the population. Pretend the sample is the population and draw multiple samples from this proxy. Basically resampling, sample the sample, each time computing the statistic of interest and giving us these sort of pseudo data sets that can ultimately reveal a sampling distribution.
Let me give you a visualization of the bootstrapping idea. I'm going to focus on the good old statistic Y bar, but again, bootstrapping can be used for other statistics. Here's the idea. We have our sample up above here. It's our one sample, and we're going to sample the sample with replacement. This is a critical point. We'll pick an observation from here, bring it down to the bootstrap sample, record it, and then put that observation back in. Thus, we again have n observations here. We'll mix them around, pick the next observation, record it, and so on, and repeat each time with recording and replacing. That once we've done that n times, we have the bootstrap sample 1, and you can see here the observations. The superscript is just indicating we're dealing with bootstrapping. We can then compute our statistic of question from this sample. In this case, we're going to compute the sample average. I'll call it Y bar 1. We'll get another bootstrap sample. We'll get another one, and all the way to getting, let's say, big N bootstrap samples. These Y bars from each of these bootstrap samples can be plotted and looked upon as our sampling distribution without using any mathematical theory. It's just a matter of repeating a sampling procedure over and over again. So it's a computationally intensive approach to finding the sampling distribution. Let's look at the rotor data again. Here we have the rotor data, the 20 observations in the first column. I produced 5 bootstrap samples. Now, if you were to do it yourself, you would get different bootstrap samples. That's due to the randomness. Notice that observations can end up being picked more than once, as you can see here with the observation of 330.212. It got picked up twice in this sample, once in this sample, once in this sample, and never got picked up in the other samples. This is due again to the notion of replacement. With replacement, you can pick it up more than once. And with randomness, you may never pick it up. We have our 5 bootstrap samples. For each of these bootstrap samples, I compute a Y bar. Here's a plot of the 5 Y bars from the previous slide. We're seeing some variation of the Y bars. Indeed, that's reflecting a sampling distribution, but we just don't have enough Y bars to see the sampling distribution in its fullest glory. So we need to do this bootstrap sampling many times over. In JMP, it's really easy to do this bootstrap sampling many times over. Here I'm going to the Analyze Distribution platform. I'm going to the Summary Statistics. Now, I got rid of all the other statistics. This doesn't have to be done, but I just want to focus on the mean statistic. What you'll need to do is point to the number. Hover your cursor on the number, then right-click, and you'll see a Bootstrap option. With that, you will get the option of how many Bootstrap samples do you want. Typically, it's 1,000 or more. I went a little extra with 2,500. What will then happen is that JMP will produce a new data sheet, and in that data sheet, it will put all the 2,500 bootstrap sample means, since that's the statistic of interest in that data sheet. I went to Analyze Distribution and gave the 2,500 bootstrap means. JMP shows us a histogram of the 2,500 bootstrap means. This is the computer-intensive approach to getting the sampling distribution. JMP finds the lower and upper limits that give certain coverages, namely 95%, 90, 80, and 50%. I've boxed off the 95%. We found earlier the confidence interval based on mathematical theory, namely the reliance on the central limit theorem, the finding of the t critical value, so that we can ultimately use the construction of y bar plus or minus t star times the standard error. All this mathematics behind the scenes to give us a confidence interval, as we can see here from earlier. Look how remarkably close in value the bootstrapping approach is to the theory-based approach. There's none of that leaning on central limit theorem, leaning on certain mathematics to get the bootstrap confidence interval, and it gives us nearly identical results. It's quite remarkable. So if assumptions aren't met, for example, we have too small of a sample size, or if we have highly non-normal data, or if we just don't have the mathematical understanding of a particular statistic, then bootstrapping provides a powerful alternative to doing inference, whether it's finding confidence intervals, doing hypothesis testing, and even finding p-values. Now, this doesn't mean we shouldn't do the mathematical theory approach, because bootstrapping can go astray. For example, what if your sample is unrepresentative? Then you're going to get a lot of biases. Let me talk about this with the last slide. We have learned that bootstrapping is a powerful alternative when mathematical theory cannot be relied on. The bootstrap method can analyze a broad range of sample statistics. There are some, however, conditions when bootstrapping is not appropriate, such as when the population variance is very large, theoretically infinite. There are various conditions where tweaks need to be made to adjust for bias. There's no cure for very small sample sizes. Imagine in the extreme, you have one observation. Well, sampling the sample is just that one observation. You get nothing out of it. So though bootstrapping is powerful, it's not magic. It can only work with information available in the original sample. Usually you need at least 10 to 20 observations. However, those observations need to be representative of the whole population. If you are not careful in your sampling and you get a non-representative sample, your bootstrapping will be off mark and not accurate. Bootstrapping also requires specialized software. Excel is not capable of doing that, so we need software that can do these computer-intensive methods. It's something I wanted to expose you to. We will return to its use later in the semester, but for now, let's put it on the shelf. Okay, that's our discussion. Hopefully I've established enough of a foundation for you to feel comfortable in the next lectures that will go now from one population to modeling. We will be seeing hypothesis testing and p-values in subsequent lectures, but this serves as our foundation. Okay, have a great one. We'll talk to you next time.